Hello and welcome to the first COMSOL tutorial for this term. My throat is in not a very good condition, but I will try to be slow and clear. So let's get started with our tutorial. You have seen these slides in the lecture. So COMSOL is a multi-physics modeling package based on finite element method. Other popular numerical methods are finite volume method and finite difference method. Dr. Kumar has talked about various model types and their classification in the first lecture. A mathematical model could be an algebraic equation, ordinary differential equation, or a partial differential equation. And we can utilize COMSOL to solve any of these equation types or combination of all the above. So let me skip this slide and this one too, and comes to this slide number 3, which is the tentative tutorial plan for this term. So today I'm going to start with the generic introduction to COMSOL, and let me just close this. So today we just going to set up a simple problem of fluid flow between laminar fluid flow between two plates, and we'll come to that problem in a bit. So this is the general tutorial plan, and I would like to mention here two resources for COMSOL help. So one is this COMSOL website, so I'll just show you quickly. So if you go to comsol.com, and then you can go click this under community, the discussion forum, and you will see this thread. It is a good resource for COMSOL help, and lot of COMSOL users post their questions on this, which are answered by other experienced users. So I encourage you to utilize this forum, and then on their website there are other model exchange and other features which are useful. So just wanted to show you this part, and other useful resources, their documentation. So which is I have opened here, it is COMSOL help. So it has very good documentation, and this search feature which you can utilize for any part you want to look for. Say I just want to show you, say search for operators, and then it will show you, for example, say how you can use differentiation operator, or like these different operators useful in your model calculation. So let me just again come back to our slides. So this is a typical workflow to solve any problem in a COMSOL. There are 3 steps. First is pre-processing steps, in which we define the model, by which I mean we will select the equations which we want to solve. Then we will define the computational domain or geometry. After that we're going to define the properties or constants or variables in the model, followed by mesh or discretization and the boundary condition settings. So once we have completed this pre-processing step, then the next step is a solution step. So it is already built in. You just need to select the polynomial function. There are always default values, but then we need to select solver type. So today we just going to go with all the default settings and just solve a very simple problem, but in the later tutorials we will play with different solver settings. So once you have solved your numerical model, then in the last post-processing step you can utilize data for plotting and graphics. Okay, so let's get started with the steady laminar flow between flat plates. So if you open the COMSOL, this is the first screen you're going to see, because our model is 2D. Let me select this as 2D space dimension and click on the next arrow. After that, these are the recently used modules, so I'm just going to minimize this, and now you can see there are different physics tabs nodes shown here. So whatever you want to solve, you can just add using this menu. So if I want to say solve electrostatic problem, I can select this and add to this selected physics. Similarly, I can choose from fluid flow, heat transfer, structural mechanics, anything I want to solve. I can simply add these modules and use them in conjunction with any other in any other physics which we have already added. So for this case, let us just start with by adding fluid flow. So it will be a single phase laminar flow. So I've selected it, I clicked add, and once you add, you'll see it has identified these different dependent variables denoted by U, which are velocity components and others. So once you have selected your physics, then again you need to click next, and in this now it will ask you to select steady type. So if you are planning to do steady state, which is our case today, so we'll select stationary and say click finish. So if once you do that, it will generate lot of nodes here, a model tree with lots of sub nodes for geometry definitions, and this is the physics node, laminar flow, mesh. So we'll go one by one to specify this problem and to solve this problem. So in the geometry, in this settings panel, you can see the length unit, so you can choose your dimensions here. So let us for time being choose the meter, which is the default one, but we can always choose micrometer or nanometer or any other unit here. So in this, now we can draw different geometries by either clicking these already built buttons on this menu, or we can just right click this geometry and add a rectangle here. Now in this we can define say width of 10 and height of 1, and then we can position it with saying say start at 0. So this base corner is your left corner for the rectangle, and let us specify this as minus 0.5 and just click this build selected part. So it has drawn a rectangle with width 10 and height 1. So we have built the geometry. Now in the laminar flow, if you go to this physics, you can always look at the equation, what equations we are solving here, and we can select incompressible flow here. The equation will change accordingly, the Navier-Stokes equation, momentum balance and the mass balance for the fluid. And you can select turbulence model type here, but right now we are solving for laminar flow, so we have just selected none for turbulence model type. Why does keep coming again and again? Okay, so we have selected the model. Now we need to define the fluid properties. So quickly we'll go to the fluid properties. So you can define it from material tab, but let us just say user defined and specify it as 1, and again viscosity, define it as 1. So our fluid properties are defined. Now next tab is the boundary conditions. So by default COMSOL imposes no slip boundary condition on all the boundaries. So and this initial values for the time dependent problems. So let me just add the inlet and outlet boundary condition by right clicking on this laminar flow node and selecting inlet by left clicking it. In the inlet, now let me select this boundary. So I clicked on this and then I added to the selection, and now on this we can define this as a normal inflow velocity condition of magnitude 1. Okay, in a similar way, again I right click here and select an outlet. Now I want to add this outlet, this boundary as outlet, so I selected it and I right click here. It will be added to the boundary selection for outlet boundary condition. Now here the reference pressure of 0 is specified. So now we have defined all the boundary conditions: an inlet, which is boundary number 1, outlet, which is boundary number 4, and these two walls at boundary number 2 and 3. Okay, now there are various meshing options where we want to divide our computational domain into smaller regions, which are in this case known as elements. So there are different meshing techniques, but for this tutorial we'll just go with the default. So let's start with the coarser mesh here, and again click on this build all button. So in the messages you can see that this mesh consists of roughly 3700 elements, and if you click zoom in here and select zoom box and go to this near this wall, so you can see by default it implements, it combines a boundary layer mesh and a triangular mesh for this problem. Okay, so again let me so we have defined mesh boundary conditions, and let us just quickly go to this study, this stationary type, and you can right click here and select this show default solver. So again, if you expand these nodes, then you can see all these settings, like in case of direct solver, we are solving using a Pardiso solver, which is a direct solver type. We can also add iterative solver, which we'll see. So we have specified our problem. Let us just right click on the study node and compute this. So COMSOL has solved this problem. You can look at the log here, and it took 4 iterations. And now let us see how we can analyze this data, or let us construct a cross-sectional plot to see the velocity profile. So for that we need to define a data set. So let us right click in the result node and right click on the sub node on data sets and click cut line 2D. So we are defining a cut line 2D data set. So we need to define 2 points. So let me give x is equal to 5 for point 1 and x is equal to 5 for point 2, and y varying from -1 to 1. So once you have specified points, you can click on this plot and it will show you the location of this line. So we have defined this cut line 2D. Now on the results tab, right click and add a 1D plot group. Now in this 1D plot group, select dataset as cut line 2D1. Now again right click this and add a line graph. In this line graph, it's already showing spf.u, which is the magnitude of velocity field. So if you click this plot button, it will show you the velocity magnitude at that cross section, along this cross section. So it looks like parabolic, although it's distorted, which is due to the mesh. So we have just set up a simple fluid flow problem between laminar fluid flow between plates. So let us just go back to the mesh part, and from coarse to, let us select, make it a normal mesh, and again you need to click this build all, and now we have selected a normal mesh. We have lot as compared to the coarse mesh last time. So now we have roughly 11,400 elements, and it is a much finer mesh compared to the last time. So now with this mesh, again I right click on the study and click compute. So now COMSOL is solving the same problem with a finer mesh. And now if you see the same cross-sectional plot, it is little bit better. Now let us try to match it with the analytical solution. So let us go back to our, so analytical solution is given by the velocity profile is 1/2 mu. Px is the pressure gradient in the x direction, y square minus h square, and h is 0.5 here. Okay, so let us go back here, and so let me add another line graph in this, and now in this expression 1/2 is 0.5 times mu, and rho we chosen as 1, and px is the variable COMSOL used for pressure is p, and its gradient in the x direction is denoted by a suffix x followed by the so p followed by x is a pressure gradient for pressure gradient defined in the x direction. Similarly, if I write py, it will be pressure gradient in the y direction. So I have written the first two terms and multiplied with the space coordinate y square minus 0.5 square. Okay, so square. So I have written here the expression for the analytical solution, but remember that this px is still calculated using your computed result. So let us just plot this, and if you plot this, you'll see it is matching, but there are some problems with this, and it is possibly due to this px term. So the solution is not accurate enough, and we can just go to the view and discretization. In discretization, if you now click on the physics node and select this discretization, it will show you what kind of discretization is used for this problem. For example, P1 plus P1 is first order polynomial approximation for velocity field and pressure field. So instead of this, if I use a higher order discretization, which means P2 second order for velocity and first order for pressure, and this is a more commonly used discretization for fluid flow problems. I select this, keeping all other things same. I'll just right click this and say compute. So now COMSOL is solving with the P2 P1 discretization for this problem. And now let us see the same plot, and now you can see the analytical solution and the numerical solution are matching. So, and you can rename these graphs. So right click this and select rename, and let us write numerical, and then you can again right click and say rename, say right analytical, and then you can do all these things like can select marker type for one. For example, let us select square for the analytical. So we can see that it is matching. So we have just solved a very simple problem. Now let us quickly see how easy it is to set up a multiphysics. So let us just add a mass transfer to the same problem, and so I'll just go to this model, right click and say add physics. I want to include mass transfer. Okay, so I'll go to this chemical species transport and select transport of diluted species and say add selected, and dependent variable is denoted by C here, and let us just finish this. So it has added additional physics node for transport of diluted species. And let me quickly show you what is the problem we are trying to solve. So we have solved for this velocity profile for the steady laminar flow. Now we are just adding a concentration problem to this. So we are adding two inlet streams with a concentration of 1 and 0, and we want to model how is the mass transfer. So so we have added this transport of diluted species. It will be solved in this equation, which is a convection diffusion equation with this convective flux and diffusive flux term, and it will be solved in the domain 1, which is this rectangle. Now again, in convection diffusion equation, it will ask for U for computation of convection term. So we can select from either we can user define, or we can select this velocity field, which is calculated from the first laminar flow physics. Now in the diffusion coefficient user defined, let me just define it as 1e minus 2, just to be in conjunction with this our geometry, because we have defined our geometry in meters. So that keeping our effective Becquerel number low, I just define it to be 1e minus 2, and you can also select these different options. So isotropic means same diffusion coefficient is applied in both x and y directions. So we have defined this diffusivity for the species C transport. Now the default boundary conditions are no flux boundary conditions for this module. So we need to define inlet and outlet. Now if you look at the inlet is a step change in C. So half width is 0, and rest of the half width the concentration is 1. So we can define such type of condition by defining using a step function. So if I right click this definition and go to functions and select this step, so it is the location where a step is applied is 0, and the step is going from a 0 to a value of 1 and because it has a discontinuity, we can use a transition or smoothing, transition zone smoothing, and let us define it as 0, 5. Okay, you can change it accordingly. So we have defined a step function here. Now let us right click this and select the inflow. In this inflow, let me select this boundary and right click, so it is added to this. And now I am saying that step 1 is my step function, which I have defined earlier, and I am applying this step with respect to the y coordinate. So which means it is applied at a value of y is equal to 0, which is the half width of our inlet. So we have defined the inlet condition. Now right click again and select outflow, and we need to again specify the outlet boundary here. So right click this, select this and right click anywhere. It will add this boundary to the outflow boundary condition. Okay, and these two walls are good with the no flux boundary condition. So we have specified the boundaries. So, and same mesh is good for the both of these physics. So let us just say compute. Now let us see if it has solved for concentration or not. So if you look at the steady step, stationary step, it is solving for both of this field, laminar flow as well as for the concentration. So in this line plot, in the surface plot, instead of velocity magnitude, if I enter C, it should plot the concentration. So this is the concentration distribution in this domain. So we have solved for concentration, and also let us add another line plot here. So 1D plot group and add a line graph, and again let us see a cross-sectional concentration profile. So I choose cut line 2D as my data set, and in the line graph, instead of U, let me just plot C. So this is how the concentration profile looks like along that cross section which we have specified, and you can change or define these data sets or any line within the domain and obtain this variable information along those lines. So, and another thing you could do is, instead of solving these two together, you can just add another steady step here, say stationary. It could be time dependent also, and in the first step we could just solve for the laminar flow. So I just cross this, and in the second step we can just solve for the fluid flow. Now to do this, let us just delete this solver, and you can just right click and say show default solver. Now if you see this solver, it has two solvers, stationary solver 1 and stationary solver 2, and if you go back here and see this dependent variables, then it will automatically use solution from solver 1 2. So it is going to use the solution for fluid flow for solving the convection problem. So with these solver settings, let us just again quickly solve this problem by right clicking this and say click compute. So for this case, time is not much different. Together also it's solved in 16 seconds. So but for larger problems it would be better, I guess. So what else? Okay, let us try a quick modification in geometry with the same fluid flow and mass transfer physics. So let us change the geometry, say right click this geometry and add a circle with a radius of 0.2 and with the center points described as say 2.5 and y is equal to 0, and you can just click this build selected to see this circle. Now you can again right click, and in the transforms you can select array. So we are going to replicate this circle. So in the array type there are two options. If you want to create a two-dimensional rectangular array or a linear array, so even in, so let us just select a linear array of size 5. Say I want to repeat this. So now it asks for input objects. I click this and add it to this input objects, and I gave a displacement of 1. So there will be 5 circular objects reproduced with a displacement of 1. So now if I say build selected, it has created using this array feature 5 circular objects. Now let us define a boolean operation of difference to subtract these circular objects from this original domain. So object to add is, we selected this rectangle and right click, and object to subtract, I clicked on this, and with control I click on these other remaining circular objects and right click. So all these 5 circular objects are added, and I'll just say build selected. So we have modified our basic geometry, so it is kind of having some kind of obstacles, and now we can analyze how it will change the fluid flow and mass transfer mixing with this change in the geometry. So let us just quickly re-inspect our physics notes just to make sure that boundary conditions are being set right. So if I go here and look at the walls, so all these new boundaries are by default wall conditions, so which is okay for this case, and inlet and outlet are same, and same with the transport of diluted species physics. So no flux for these new boundaries, the default boundary conditions, no flux is applied, so which is the right boundary condition we wanted to apply. So with these boundary conditions, let us just right click this and select compute. So you can see how easily we have modified geometry and studied the same set of equation, and so these are the results with the changed geometry. Okay, so similarly we can do lots of different type of studies. Okay, so let me see what I have here. So we have completed this part, and so these are some exercise problems for all of you, and just try these out, and in the next tutorial we'll look at the linear and non-linear equation solution in COMSOL. So with this I think we have solved a simple problem. Then we have seen a multi-physics implementation, how quickly we added the mass transfer to fluid flow, and then we solved a geometric modification, a problem with geometric modification to the same set of equations. So if you have any questions, please feel free to contact me, and with this I'll stop this first demo for COMSOL. Thank you.